Hello, here in Chemistry in Action, we've just brought you through a series of lessons in organic chemistry which took us from the simplest of the organic compounds, the hydrocarbons, to hydrocarbon derivatives containing oxygen, nitrogen, and the halogens. From there, we went on to study gigantic organic molecules, the natural and synthetic polymers which we use in various materials. Lastly, we learned about the biological polymers present in all living things. Today, let's change direction a bit and begin a discussion on the environment. We all know that word, but what constitutes the environment? It includes air, land, water, and other forms of life that surround us. In this lesson, we will focus on the atmosphere, the gaseous envelope that surrounds the Earth. We will look at the chemical nature of the components of the air, the role of the atmosphere in maintaining heat balance of the Earth, and chemical changes in the atmosphere that affect us locally and globally. More after these reminders. The gaseous mixture, which we call air, is an integral part of our planet Earth. It moves with the Earth in space as our planet revolves around the Sun and rotates on its axis. The total mass of the atmosphere is estimated to be 5,000 trillion metric tons. Most of it lies 32 kilometers above the Earth's surface. Half of this is in the lower 5.5 kilometers. The atmosphere extends to about 500 kilometers. Traces of gas molecules are found higher than this. This chart shows the composition of dry air, that is, not including water. It is 78% by volume nitrogen, 21% by volume oxygen. This means every time we take a breath of air, every 100 molecules are made up of 78 molecules of nitrogen, 21 molecules of oxygen, and 1 molecule of another gas. Oxygen is one of the most important gases found in our atmosphere. It is slightly soluble in water, 4% by volume, and sustains marine and aquatic life. Thus, oxygen is found in the atmosphere, lithosphere, and hydrosphere. Nitrogen, as present in air, is relatively inert. It acts as a diluent for oxygen in the air. Without it, every spark would ignite every combustible material around it. Oxidation reactions would occur many times faster than they actually do. Energy from lightning or heat from a supersonic transport jet or the engines of cars can split nitrogen. The nitrogen atoms may then combine with oxygen in the air and produce nitrogen oxides, which react with moisture in the air and produce acid rain. The other components of the air are argon and other gases in trace amounts, including carbon dioxide, neon, helium, krypton, xenon, ozone, methane, oxides of nitrogen and sulfur, and other gases produced by man's activities. The composition of the air is fairly constant in different locations, but it does change with time, especially in the amount of trace gases. An important gas in the air is water vapor. In high cold regions, it can be less than 1% by volume. In hot, humid places, it can be as high as 4%. Water vapor keeps the temperature near the Earth's surface within a habitable range. Water molecules absorb excess heat from the atmosphere upon vaporization, store this energy, then release it upon condensation. Thus, at any given time, the latent heat content of the atmosphere is determined by the amount of water vapor present. The atmosphere acts as a heat engine by converting heat received from the sun into other forms of energy. If not for this, the Earth would continue to grow hotter as it received more energy from the sun. Climatological data indicate that the Earth does not show any net heating or cooling. This means that the Earth emits the same amount of energy that it absorbs. We note that the law of conservation of energy operates on our global system. The atmosphere has 5 zones based on a temperature gradient. The troposphere, or the lowest zone, extends to about 12 kilometers from the Earth's surface. Dense cold air in the higher altitudes of the troposphere tends to sink and replaces the lighter hot air, which then rises. This vertical movement mixes the air fairly well in this region. Chemical species are dispersed easily and have short residence times in this region. You probably remember that the effects of the 1986 Chernobyl nuclear accident were felt in other countries far away. Similarly, ashes from the 1991 eruption of Mount Pinatubo circled the globe. The stratosphere extends to about 50 kilometers from the Earth's surface. The air here is not exchanged rapidly with air in the troposphere. Ozone is present as a layer in the stratosphere, starting at about 18 kilometers above the Earth's surface and extending to about 40 kilometers and beyond. Most jet planes and supersonic transports fly efficiently in this region due to the absence of turbulence. Short wavelength ultraviolet radiations, 200 to 300 nanometers, can penetrate the middle region of the stratosphere, but are mostly absorbed by oxygen and ozone molecules. This energy is used for air circulation 30 kilometers above the Earth's surface. The third zone is a mesosphere, which is in the region between 50 to 90 kilometers above the Earth. Here, there is a decrease in the amount of energy-absorbing species, particularly ozone. Some ions of the oxygen molecule, O2+, and nitric oxide, NO+, are formed when ultraviolet rays hit neutral oxygen and nitric oxide molecules. The fourth zone, or thermosphere, is the region 90 kilometers above the Earth's surface. Radiation of wavelength 100 nanometers can penetrate this region down to about 200 kilometers above the Earth's surface. Ionized chemical species like O2+, O+, and NO+, produced by the bombardment of cosmic radiation, enrich this region. The thermosphere and the mesosphere are collectively known as the ionosphere. The chemical species in this region play a significant role in long-distance communication since they are capable of reflecting radio waves. Time now for us to take a break. We'll be back to talk about the changes in the chemical composition of our air.